Hi, everyone. We are Group 5, and our project was to investigate the effects of motion on CT image quality using parallel beam and fan beam reconstruction. So a background on CT imaging. CT is an X-ray imaging procedure where narrow X-ray beams are aimed at a patient and quickly rotated around the body, producing signals that are then processed by a computer to generate cross-sectional images. Each X-ray line integral gives a 1D projection of a 2D cross-section of the body at any angle. So we take a collection of these line integrals across hundreds of angles to then reconstruct cross-sectional images. This transformation across many angles is known as the 2D radon transform, and we can collect all the projection data into a sinogram to visualize it. The inverse of the radon transform is what produces the actual 2D cross-sectional image that we see above. So the two types of reconstruction projections that we analyzed in this project were parallel beam and fan beam, and we will be comparing those to the original images. Parallel beam projection was used in the first generation CT scans. Basically, the X-ray source and detector are parallel to each other, producing single line projections from the source to the detector. So after it produces one ray, both the detector and source will move over and do this many times just for one view. This process is extremely slow and many rotations are needed to get sufficient data. Fan beam projection became the better version that was used in third generation CT scans. In fan beam, there's only one source that produces multiple line projections across to the detector. So instead of producing one projection and shifting it over and over like in parallel beam, this will produce a whole view all at once. So each rotation occurs much faster and the CT imaging process is more efficient.
So, complex motion can change CT quality dramatically in different scan. And an artifact can occur when there's a voluntary or invalid verification within the training the image required, and it's called motion artifact. Most artifacts can be appear as slurring, streaking, or fading. On the right, you can see there's a motion artifact happens in those two sliding arrows, where physician actually make a false connection on the patient when your patient is fully fine. And there's several ways to reduce the motion artifact, including faster scans, more detectors, or special reconstruction technique, or just slow accurate elevations. In our simulations, we're moving the input shifting x-axis and shifting the y-axis. We're doing this in one or multiple steps. And the thing that we choose are the small square phantoms from the large square, the classic Logan phantoms, and the clinical heart data that's shown in class. And our primary simulations involving mallet functions such as a radon transform and an iRadon functions that create sinogram and reconstruct the image with parallel beam, and a fan beam and I-fan beam function that creates sinogram and reconstruct the image with fan beam calculations. We're doing this in multiple shifts across the rotation of the transform, taking the positive x and y directions.
All right, so now we're going to go through a series of examples that we've generated using our MATLAB code, sort of as Barrett described. So for this one, we're just going to look at the small square phantom or a series of impulse points across the plane, and we're moving them over one step, so an instantaneous shift theoretically of 10 in the x direction. For our parallel beam, we elect to do 360 degrees just to illustrate the point of sort of an interesting series of artifacts we found. Is that in the parallel beam reconstruction, there's a sort of clear doubling effect. In our simulation, as you can see here, I'll zoom in on it. And you can see a break in the sinogram for that as well, if we get to. Whereas in the fan beam, there's a slight doubling here, showing a theoretical shift in the motion during the scanning. However, it was less apparent in the vertical column in the middle, something that we'll continue to see from our simulation, which is an interesting phenomenon we observe. So as you can see in the sinogram, there's some breaks here illustrating where the shift theoretically occurred during the rotation based on our simulation. So here's another phantom using two squares with one shift and in the y direction. You see a sort of doubling effect again in the radon transform. Whereas in the fan beam reconstruction, we see more of a blurring streaking effect that causes more noise in the image. I think this has to do as well with the rotation group we chose for the radon. which is something that we might want to investigate more, using different parameters in the future. So as you can see here, the doubling effect in the middle and the streaking and sort of shadowing effect, which is one of the types of artifacts that we saw in the Phantom reconstruction. So now we move on to the Chef Logan Phantom, which is an inbuilt Phantom for MATLAB's imaging suite. So as can be seen here, we have the original image in the top left that we've been discussing. We have one shift instantaneous in the Y direction, and we can see the fan beam and parallel beam reconstructions. The fan beams have slightly less blurring and more of a streaking effect as compared to the parallel beam reconstructions here, which is again supported, shown throughout many of our tests here for these instantaneous shifts. So now we're going to do a more gradual shift. So we're doing 15 steps of one shift evenly across the interval of scanning. So we have the original Phantom here. So it's 15 shifts and then one is each of 1 unit or 1 pixel. So it's 15 total units in each direction, moving to the bottom right corner. But with the parallel beam construction, we can see significant blurring, streaking, and breaking of the edges of this Phantom. Whereas in the fan beam reconstruction, there's significant noise and streaking occurring off the edges radially, related to the nature of the fan beam that appears. So here's an interesting case that we wanted to say, is it one point in the image moved? So in this, we can see in the top left, the original Phantom image, with the top left square being slightly offset from the other two, and then moving just that square slightly over, which also illustrates the nature of the sinograms for these, as we've discussed by some of the other groups. You can see that there's one of the 3 sinograms for this image is affected, or one of the 3 lines in the sinogram is affected by this motion, as the other 2 remain stationary and the points are held into place. So for the parallel beam reconstruction, this shift we like to have it start at 90 degrees, which is something that we would like to study more in the future, where we had, how do we have more time to run simulations at different starting points. So we can see some blurring and streaking vertically, whereas with the fan beam, you can see a significantly more radial streaking across the image. So you can see some of the differences in parallel and fan beam here. And this is one shift by that 1 point of 10 instantaneously at that point. So here's an interesting thing, something we wanted to look at using the part data that was given in class, the example coronary patient tip. If this image was moved slightly, you can see the clear effects of motion on CT imaging, with blurring and streaking occurring in these 2 images, causing a lot of the structures to be significantly less clear and harder to interpret, which relates to many of the clinical effects we have been discussing. So as you can see in the parallel beam reconstruction, there's significant blurring, and it's much more difficult to make out many of the structures in the image. And with the fan beam, you can see some of the radial artifacts, as well as the degree of blurring, which would affect the ability of an image like this to be read, relating to some of the issues that are caused by motion in CT scanning for clinical purposes. Here's a little simulation we ran, moving a total of 30 units by these 2 different Phantoms across a number of different steps. So this is how the image varies in terms of the theoretical magnitude of each step in the motion, sort of simulating a gradual motion across it. This is an elementary way to look at it. However, we thought it would be an interesting thing to look at using our MATLAB code. So it's moving a total of 30 units in the X direction over 1 to 10 total steps evenly across the interval of scanning. As you can see, many of the artifacts are similar across that we've been seeing based on these reconstruction methods. However, there are slight differences across each magnitude of step that result in different artifacts, indicating that there is some effect, or there is significant effect of the motion and the graduality of the motion across the image, which would be interesting to observe and study further. So here are references for a lot of clinical stuff we discussed in the beginning. And thank you for listening.
Great. Oh, those are cool simulations. Any questions about that? So it looks like when it's a fan beam, looked like you actually shot out a bunch of streaks in different directions, whereas in a parallel beam, it looked like a superposition of 2 images,
Yeah,
right?
that's
That's-
something we consistently noticed across our simulations as well. However, I think that may have been related to exactly how we ran the simulations for parallel beam, which was something I was getting used to. And
Yeah.
I think all of us were in the MATLAB code in observing what the appropriate number of degrees to rotate over, so I think
Oh,
that
yeah.
like, might be changed at 180 degrees for,
Sure, sure. A lot of it depends, the relationship of the motion to what the trajectory of the gantry is in that motion direction at that time. So,
Yeah.
yeah, let's,
So just to like go over, I guess, for your methods, I noticed that there are these really like sudden abrupt shifts in the sinogram. I'm guessing that's because like you computed part of the sinogram, then shifted the
Yeah,
image,
yeah,
and
that would be-
computed the next part and so on.
yeah, that's,
Would you say that that sudden shift is accurate to like how motion would look in a clinical setting?
I would say no. I would agree with that, and that's why we wanted to look at some examples of having multiple steps in the motion across the image evenly. Not that would be perfectly accurate either, because in reality, motion is continuous.
Mhm.
Yeah, motion is theoretically continuous. So our simulation, I would agree, is somewhat elementary or naive, but we were trying to use it to observe some of the characteristic patterns, I would say, but you are correct. And I can't remember, one of the papers we saw discussed the speed of motion that would be required to create a large artifacting, especially considering the size of the detector. So that's something that might be worth considering in a clinical setting or beyond our simulation. So